There's different ways to set up sweeps as well, so you can do that with bandwidth. You've got IF bandwidths. My advice is, if in doubt, leave them as they are in the default settings, but you can change the sweep times. You can modify them. You can also do things like this smoothing as well. So if we go back to, let's go back to the scale, set that back to 10 dB. And you can see that now, if we go to bandwidth, you can do all kinds of funky things like this and remove all those large variations. So smoothing can be quite useful as well if you're trying to make band stop measurements. Where's the actual band stop response of the filter? Because that isn't everything. That's just the noise floor of the instrument that's interfering with what's really going on. So you're somewhere around about that average point.
So how does it smooth it out? It does what?
It's filtering. It uses an additional filter inside the instrument at the IF bandwidth. So did you go through the theory of VNAs as well?
We didn't, no.
So you're doing a down conversion essentially. You have a high frequency here, which you pass through your device, and then you do a down conversion. So a mixer is doing that. There's a mixer, down convert to an IF, and all of this video processing here, so you can see it on a screen, is done at an IF frequency. This is not the actual frequency that's passing through. It's a down convert, yes. And you're modifying the IF signal so that it's cleaner, and you basically are putting a low pass filter. This is probably a DSP algorithm that's doing this here. It's not a physical filter, but it will be an algorithm, a DSP based one.
The digital algorithms are sometimes better than the physical ones.
Yes, and sometimes no as well, but that's a whole different story. Yeah, so I think we've covered most things. Sweep, you don't really need to worry about that. You can use the default ones for the measurements you're doing. But the other thing you need to bear in mind is, I'll get some cal standards, so when you hit this cal button, we're going to use response cals. We don't have these mechanical ones for now. And you've got these open and short circuits, and I'll give you a homemade one, if you like, to do these. You're not going to have a perfect measurement. We can do it here as well under mechanical. I can make some rough ones to do this, and you'll have an open, a short, and a load. So what you'll do is you'll do all of the calibrations on this pot. You'll do the open, the short, and then the load on this pot, store everything. Then you swap to this pot and you do open, short, load on here, store them, and then finally you do the through cal, which is the normalization. Okay? And that's all of it. That's all the calibration done. There is also
what about isolation? There
is an isolation cal as well. You never need to use that. I've never needed to use the isolation cal. I've just done full 2-port. So that's 3 standards on each port, and then the through, and you can do any measurement you want. The isolation calibration, you shouldn't need to do it.
Okay.
All right, and that's it.
What is the through is to see if there's any coupling between the 2 ports, right? And then the isolation is for...
The through sets the baseline. The through sets the baseline for transmission, because you're going to get lost through these cables, right? So you need to calibrate out those losses.
Okay.
So when you do the load, you are looking at the standing wave along this cable to this interface. And through clever matrix mathematics, right, all of that information for the short and the open circuit, it cals to this interface. And when you put the through in, it's basically telling you the loss through the entire transmission, the transmission path, backwards and forwards for S21 and S12. And then it's all done through matrices inside this instrument. With a nice, it probably is a DSP function that's doing it all. It does all the matrices mathematics, and you end up with nice flat lines for everything.
Okay.
So when you put a load, when you put the load that you've calibrated to on here, it will be perfectly down at infinity. Okay? In practice it isn't. It isn't really down at infinity. It's just because of that. It's said, right, I understand this cal, I know everything about this particular cal standard, and I'm doing everything reference to that cal standard. Do you understand? So everything is actually referenced to the standards that you put on these interfaces. That's
you'll
what
have
you're
a different.
measuring
You'll
to.
have a different impedance compared to the termination.
Yeah,
net.
but because you've used a reference standard, that standard is the same for a guy who's got that same instrument or a similar instrument in the United States as someone who's got it in China, so that you'll get alignment with your measurement results. So if we took a measurement here using those CAL standards, someone else takes a measurement in another country using a similar instrument and the similar sort of CAL standard, they're going to get close to that same result. Okay? But very difficult to get a true absolute accuracy because you're using those standards. So you can imagine now how tight the tolerances need to be on the actual perfect standards, and that's why they're expensive. That's why you're talking thousands of pounds for those CAL standards, because they have to be repeatable across the globe. All right? Have you got enough to be able to do this now?
Yep.
Have you got enough to get started?
Yeah, I
you
think
sure?
now we will be able to.
You don't need to be worried about blowing things up, because if you're not using amplifiers and you're just using passive circuits like these, you're not going to blow anything up, okay? It's impossible, frankly, unless you do something ludicrous and put a power supply on an antenna array, which I don't think you're going